Yeah. So are you able to see
Yes,
my
sir.
screen?
Yes, sir. Is it visible?
Okay, thank you very much. So let's start the presentation quickly. Yesterday we wasted a lot of time. So today I hope I will be able to finish my presentation in the given time. Okay, the topic of my presentation is advanced analytics in process metallurgy, data-driven models. So, and my name is Dr. Amiy Srivastava, and I am a process engineering specialist at STELCO, as a professor said just now. To introduce me, let's get into the topic of discussion. So, outline of the presentation, what I'm going to talk about today. So, firstly, I will give you a quick recap of previous class, what we learned yesterday, and how am I going to connect the previous class with this class. And then in this thing, I'm going to talk about the details of some physical models, then development of correlation equation. So we always talk about machine learning, but like past days, like 10 years ago, or if not 10 years ago, I would say 20, 25 years ago, that time people were not that much aware of machine learning techniques or data-driven techniques. So that time people were using very simple multilinear regression models, or they were developing some equations using some mechanism modeling techniques like thermodynamic principle and some equations, and they were using some very less amount of data they were including, and they find out some equations. So we will go back to past. We will see how people were making the equations back in the day, and then we will talk about how we can improve those equations if we apply machine learning to improve the model accuracy. And I will talk about bubble-related process models. Like yesterday, we talked about we just touched upon bubble-related process models, but today I will give more details about this. So once it is done, it will cover the major part of my presentation. But after that, I have kept some time for dephosphorylation model. So we developed this data-driven model 2, 3 years ago, I believe, and that was quite useful for different people in industry as well. So I will talk about this thing. And the third one is our latest model, which is called hybrid endpoint prediction model. I will tell you why we call it hybrid model and what is all about it. One thing before getting into the presentation, I would like to tell all the students or everybody who is listening to my presentation that I'm not going to get into the algorithm of machine learning. I will try to explain the application of machine learning in process metallurgy, because algorithms you can find out, you can develop the codes, and libraries are available in GitHub, so you can write your own codes and you can assess the performance of your model. You can check whether your model is overfitting or underfitting. Those things are already there. But how that those models can be implemented in the field of process metallurgy, that I will talk about today. So let's move on to the next slide. So this is something I showed you yesterday. So the yesterday's class was totally image analysis based. So we have seen many videos yesterday, many process models. Like this was the example of Tundish process model. This was the example of mold physical model. That was the example of image analysis. Then we talked about what is image, like how image is segmented or and how the image is studied. Basically, image is a form of cluster of pixels. And then what was depth of field, what softwares were used, can be used to process the image, what are the applications of image processing. So those things we learned yesterday. We also learned very interesting thing yesterday, that in such physical models, we have to use shadowgraphy, because the background and foreground should be distinct, and then only image processing softwares can sense or can analyze those objects. So that's why we implemented shadowgraphy. So we talked about shadowgraphy yesterday a lot. Then we introduced and compare between basic and advanced image processing techniques. I told you like when we can use basic image processing techniques, and when we cannot use image processing techniques, and we have to move to advanced image processing techniques. So those things I explained clearly yesterday. Then I explained how machine learning can be implemented in image processing, and that is basically the part of advanced image processing technique. So that was all about the yesterday's lecture. Now let's move on to the today's lecture, like the fresh start. Okay. So again, my style of giving any lecture, delivering any lecture is like I explain the things clearly, so that you can know the application of the advanced algorithms, and then because then you will be having a feeling of that. So let's start with the topic. So the case study one, which I was talking about, the bubble related phenomena. So as I told you that organ gas is injected into the continuous casting mold in order to avoid SEN clogging. SCN clogging can be removed by organ injection, but at the same time, we produce different type of bubbles. Some bubbles can be very big, some bubbles can be very small. So bigger bubbles have sufficient buoyancy force, and they can be moved to the top of the mold slag layer, like here. They can be moved easily, and they can be removed from there. Although when they are removing, they create open eye. But the smaller bubbles, they are driven by the flow of liquid steel, which is coming from the tun dish to the mold, which is introduced from the tun dish to the mold. So those bubbles are influenced by the liquid steel flow, and those sometimes they reach close to the side wall of the mold, and over there they are captured by the side wall because solidification is also taking place at the same time. Arka, you raised the hand. Do you want to say something?
No, sir, please go ahead.
Okay, thank you. Okay, sorry about that. Sorry for the interruption, guys. Yeah, so these bubbles are entrapped, and they can create a lot of quality issues like blister, pencil pipe, all these things. So what happens here? I have made like a kind of an animation for you guys to understand. So what happened when we produce bigger bubbles, like those bigger bubbles can be of 2.5 mm to 7 mm. So those bubbles are basically it is they are less likely to reach the narrow wall of the mold. So they can, because of the high buoyancy force, they can reach the top layer, and over there they create uh, kind of an open eye, and that open eye from because liquid steel is exposed over there. So our atmospheric oxygen can be entrapped, nitrogen can be entrapped like into the steel, and lot of exogenous inclusions can be formed. So this is something we want to avoid. We don't want such bubbles which are very large in diameter and which can create these type of open eyes, because those are detrimental to the quality. And very one thing I want to tell you that if we have those inclusions in the tundish, we can remove them because we have a chance. We have some residence time over there. But if we have those inclusions in the mold, we don't have chance because solidification is quite rapid over there. It is like some some removal of inclusion has been observed by researchers, and some is actually happening, but the extent of that inclusion removal like in the mold is way less than that what we see in our tundish. So that's why we don't have much time over there, we don't have much residence time. So if we introduce new inclusions over there, so it is more likely that we are going to produce bad quality steel. And I told you, like, what is the dollar effect of producing bad quality steel? So we cannot afford producing bad quality steel. Okay, let's move on to the next slide. Yeah, so you can see this type of open eye can be formed on the both side of the top layer, both side of the SEN. This is our SEN. Like this is the top view, and this is the here you can see the front view, and you can see one open eye is formed here, and another open eye can be formed here. And these are the places where from oxygen can be entrapped into the steel. So, and when it happens, when bubble size is like one scientist, like one researcher reported, the size of the bubble should be around 1.5 mm to 2.5 mm. But it has in some studies it has been seen that if we have 7 mm bubble, sometimes bubble coalescence take place, two, three bubbles like they come closer to each other and they create a bigger bubble, and then bubble diameter increases to 7 mm. Sometimes it has been seen, and because of that, that open eye can be formed. Now, what happens when we have the smaller bubble? Smaller bubbles, like the diameter is very small, like 700 micron, 900 micron. So, because less small bubble size is smaller, so less air is there inside the bubble, so buoyancy force is less over there. So, what happened? Like those bubbles are basically influenced by the by the by the liquid steel flow, like inertial forces, and like so they are not able to surface up. They cannot go up to the slag layer, and they go to the narrow wall, and like sometimes they accumulate over there, and if the accumulation increases, so that time what happened, like because the solidification is going on, so those bubbles are captured by secondary dendrite arm spacing or primary dendrite arm spacing, and we get blister defects in our slab, and we don't know because those are kind of soft surface defects, because they are not visible from the surface. And sometimes if you don't do scarfing from the edges of the slab, so what we have, like we cannot and if we don't inspect it, we cannot find it, and then once we roll it, we see that lot of pencil pipe defects are observed on our plates, and pencil pipe defects are not acceptable by any customer. So we have to reject that material, and there is again coming a dollar loss, and which is not acceptable. We cannot afford it. Now you can see, like from the image, like initially we have these bubbles are entrapped over here, and once we roll it, those smaller bubbles, like those bubbles, entrapped bubbles, are converted into pencil pipe defects. And some bubble size defects and the size of the bubbles would be like 100 micron to 750 microns. So what you can see here, like what important thing, there are many important things, and if we study those things, we can avoid having these defects. Firstly, we avoid injecting organ, but it is less likely to happen because SEN clogging is, people can remove or can reduce SEN clogging by means of calcium wire injection or calci wire injection. But still, some inclusions are there. So because of the inclusions, in the extended period of time or prolonged time of casting operation, and these days we want to produce a sequence length of 17 heats or 18 heats, something like that. Maybe for slab caster, we produce 12 heats, 13 heats in a row. So it is likely to happen. Like SEN clogging is always there, and it is very difficult to avoid SEN clogging. On the other hand, if we inject organ gas, so that's why we have to inject our organ gas. On the other hand, like negative pressure is generated inside the mold, and that can and nitrogen can be entrapped from any pore or any opening or joints, and organ can create a gas curtain inside the wall of the SEN, and that can help uh, to further reoxidize the steel. So that is another reason we have to use organs. So what else we can do here? Like we have to maintain the gas flow rate or liquid flow rate, so that we don't get we can avoid such bubble ranges or such bubble distributions which are detrimental to our quality in terms of blister defects or open eye formation. So, but that type of optimization is needed, and kind of a research project is required to do that. And that's why we did this research. So, what we wanted to know, basically, we wanted to perform an optimization study, and for that we wanted to develop an equation, and which can tell us, okay, this particular process parameter, for example, viscosity, or I would say surface tension, is affecting the mean bubble diameter of the mean bubble diameter inside the through the width of the mold. So mean bubble diameter. So we wanted to develop an equation like that, which can help us identify, like if the mean bubble diameter is increasing, it means we are introducing more and more bigger bubbles, and if mean bubble diameters are reducing, it means we are introducing more and more smaller bubbles. So it should be somewhere in the center, and it should not be very high or it should not be very low. The exact value nobody knows because this is still a research topic of research. But yeah, from the previous research, like what people have done to identify, because as I told you that these physical models are the replica of steel plant, like real mold, and real molds are basically opaque. We are not able to see over on it. We are not able to see anything over there. So what happens, like whenever we have blister defects, we take our slab, we we crop that slab and we see the we perform a macroscopic analysis like visual inspection, and we measure the size of those pores, blister defects, and then we can extrapolate that okay, our bubble size would be this much, and because of that we have got this big blister defect. So that is one way of identifying the bubble, but that is not giving us a holistic idea of the actual bubble size. We only know the bubble size entrapped in the side wall of the or narrow wall of the surface, but we don't know because the process is quite dynamic. And whenever we take a slab offline and we crop it, that situation is telling us anything about only one particular timestamp. Like maybe that thing was that thing had happened at time t is equal to t, in between time is equal to t1 and t2, like for 1 minute, or maybe not 1 minute, 1 second, or 2 3 seconds. But we wanted to have a holistic phenomenon. The data which we are collecting from just from 1 second or 2 seconds, it is very difficult to identify like what exactly is happening over there. So we thought that we should start developing an equation. Maybe during my PhD, it is difficult to finish the analysis, like which can be replicating the real plant mold. But yeah, we can reach near to that thing. But then another researcher will come and he will proceed from that point where I left. So I performed some literature review and I found some expressions for the bubble diameter. So I found there are two types of liquid basically. So one is basically stagnant liquid. So stagnant liquid, like no fresh liquid is introduced into the reactor. Sorry about that. So, I mean to say, if I take the example of a ladle, in ladle we don't introduce any liquid from outside. We have liquid already there, and then we inject argon gas like by means of plugs, and we produce bubbles and for effective mass transfer of inclusions. So that thing we do in general. So we can call it a stagnant liquid. Although localized in a localized way, we can see that some liquid still is flowing inside. Some recirculating flow patterns are there. But still, we can call it stagnant because no new liquid steel is introduced. So these equations, like people have developed for such stagnant liquids. So, like this is including all chemical engineering research and metallurgical engineering research. All these research are included here, and I have found these many equations for mean bubble diameter or initial bubble diameter. You can see like how bubble diameter is dependent upon the gas flow rate and inner diameter of the nozzle, and then outer diameter of the nozzle. And there are many factors here. Many scientists have developed like long back. This research is still going on. Like you see, the first paper was published in around 1956, and then here like this one is the latest. After that, also I have found some like till 2005 we have got some equations here, but those are all stagnant liquid correlations. I realized that my problem was, and yeah, all these equations I have jotted down in my paper, and this is the screenshot of the paper. So if anybody wants to find out, like to perform another literature review, they can refer this paper. So yeah, so but my problem was related to the dynamic kind of a moving liquid, because all the time a new liquid was introduced from the tundish, and so one more parameter was introduced that is called the velocity of liquid steel or velocity of liquid. So that parameter was not there in the previous studies, and I tried to find some equations for that also, and I found these many expressions. And here we can find that people have used UL. UL is basically liquid velocity. People have used UL. UG is gas velocity. So they have developed. So till 2020, people are developing, like doing research and developing these equations. So I realized that, and also these equations are not from, these are from bubble column or from different fields, but no study was found which provides a correlation equation for the mean bubble diameter for mold. No, so I realized that I can contribute to the like scientific community if I if I do something for the mold. So that's why I decided to do that research. So I wanted to perform bubble size distribution like parametric study, and then for that bubble size distribution can be used as an indicator. As I told you, like for the like bubble size distribution or mean bubble diameter can be our one of the indicators which are telling us like how which what type of bubbles are introduced in the during the process. So if bigger bubbles are introduced, open eye can form, as I told you. If smaller bubbles are introduced, blister defects can form. So BSD needs to be approximated by a single scale parameter. This is another thing. Like we might be having different parameters like average, mean, median, standard deviation. Many of the things can be there, and we were getting like a distribution, like histogram plot. But how like we will perform that time I did not know like how will I perform a parametric study using the histogram type of data. So I thought that I can convert that histogram into a single scale character, and I called it like single scale characterization technique. And then we use Sauter mean diameter, and Sauter mean diameter. You can find out the definition of Sauter, why we use Sauter mean diameter. Like all the researchers in this field are using Sauter mean diameter. They are not using just average diameter because shorter mean diameter gives a better idea of the process, like in terms of bubble diameter. So this bubble diameter is the function of gas flow rate, liquid flow rate, surface tension of the liquid, then viscosity of the liquid, and density of the liquid. One more term was there. I have found in some research, like people have introduced the density of the gas as well, like rho g. But I did not include that because I could not add any more gas. I could add during my experiments. I added only one gas, so that is the limitation of my model. Then what happened? Like I decided to perform a dimensionless analysis. That time I was not very much familiar about the machine learning thing. So my professor told me that we have to capture non-linear correlation between these parameters. So we cannot just perform simple or multilinear regression. Like we have to find out. We have to do something which can capture non-linear correlation between the input variable, like independent variable and dependent variables. So that time I thought that I should make a dimensionless analysis, and one good thing of the dimensional analysis was I find out an equation, like and I can like my equation can also be compared along with those scientists who have already developed those equations before. So I tried. And now I'm going to tell you like how I developed this equation. So you can see like this Sauter mean diameter is a function of gas flow rate, liquid flow rate, surface tension, viscosity, density of liquid, and I took one term like gravitational acceleration so that I can identify my equation. And then here we did like total number of dependent and independent variables. In so this is basically the methodology. Like in some YouTube videos, in some NPTEL lectures, I found like how we can apply dimensional analysis. So I included that in my paper. So the method is basically very simple. Like we have to identify how many total variables are there, so like including dependent and independent variables. So you can see here six variables are here and seven here. The total relations we have seven, and these variables and their respective dimensions are basically I just wrote down the dimensions like L is the dimension of D3. This is kind of basic high school mathematics, high school physics. And then basic dimensions are MLT. So the number of basic dimension is M is equal to 3, because like in all these expression we have M, L, T, so we have 3. So we wanted to develop pi groups. So like those pi groups, like we need to know how many pi groups we have to develop. So that is 7 minus 3. 7, this number is 7 and this number is 3. 7 minus 3 is equal to 4. Now identifying the repeating variables. Now we are going to make the pi group. So before that, we have to identify what are those repeating variables. So there are some rules of identifying those or selecting those repeating variables. So firstly, we need to see they should not be dimensionless. So we cannot take any repeating variable which is dimensionless. And then they should have all M, L, and T dimensions combined. They should not be dependent variables. Like we cannot take D32 as our repeating variable. and then none of the repeating variables should be of same dimension. We cannot take two repeating variables which are of same variable. Otherwise, we will be losing some information. Let's see the next one. So based on the above rules, I decided that I will take these three repeating variables. Oh, this is basically new. It is not new, it is new. There is a mistake over here, printing mistake, typo. And then writing the pi group. So this is how we wrote the pi group. So these repeating variables are basically repeating in all the pi groups. Pi 1 also you can see these three, pi 2. In pi 2 you can see these three variables. In pi 3 you can see these three variables, and in pi 4 also you can see these three variables. And for the fourth variable we can take rest of the variables one by one. Like in the first expression I took D32, in the second expression I took QG, in the third expression, I took QL. And the fourth expression, I took G. And then we will write down the dimensions of all these pi groups. And here we can say, and this is the power of A, power of B, power of C. And let's move on to the next slide. So this is how I wrote the dimension of pi 1, pi 2, pi 3, and pi 4. Now, what happens, like value of these constant can be calculated for each equation below. So if you see, if you go back to the previous slide, we have like, we need to know like what is the power of L. So L, like on the right hand side, we have the power of L is equal to 0. There is no L over there. Or yeah, and so here we can say minus 3A plus or minus B and plus 1 is equal to 0. That's how I wrote the. That's how I wrote all the equations here, and like these are simultaneous equations, and I solved these simultaneous equations to identify the value of A, B, and C, A, B, and C, A, B, and C for all the equations. Then I again plugged in those values here, and I found pi one. This was my first term. This pi two was my second term. Pi three was my third term, and pi four was my fourth term. And then I could write down my equation like this. Like this is basically your dependent uh, de- uh, this was our dependent variable, and these are all our independent variables, independent pi groups. So I could write. So you can see, mm, yeah. So this is the first one is over here, and second, third, fourth here. I could write this way. So, I will show like how we could write this way. Okay, so here we have pi 1 is equal to this one, pi 2, and pi 1 is basically dependent variable because D3 2 expression is coming over here. And here we have like these are, and here we have, okay, one more mistake is here. I wrote input here and output here. It should be flipped. So basically we are getting D32 value as our dependent variable. So it should be output and it should be input. Sorry for the mistake. And then if you see here, pi 2 is equal to this expression, and we can write down this expression in this way, like pi 1 is equal to, like when we break that function, like what expression I wrote in the previous, yeah, here, like D32 is the function of this one. So when we break this equation, so we can write an expression like this, and then we can take the log ln on both the side, then and then now what we need to have, we need to know, we have these value pi 2, pi 3, pi 4, and we need to solve the values for A, B, and C and K. If we can find out the value of K, A, B, and C, we can find out our equation. Let's see how I found that thing. Yeah, but before getting into that, I want to explain a little bit about the model, like what type of liquids I took for capturing data, and how I took the images, like what type, and so that type of thing I wanted to show. So I took basically four different liquids. So I took tap water. Why I had to take four different liquids? Because I had to change surface tension, viscosity, and density of the liquid. So that's why I had to take four different liquids. And because tap water surface tension, I could measure. I had the facility in my lab, so I could measure the surface tension and viscosity and density of these liquids in the lab. So, like I took tap water, soapy water, and then silicon oil. Two different type of silicon oil. One silicon oil was having the viscosity of 5 cp, and another silicon oil was having the viscosity of 10 cp. And then I performed a lot of experiments, maybe like 200, 300 experiments I performed. And then I took the image from each experiment, and like this type of bubble images. and I captured the mean bubble diameter from each experiment. People may ask like how I captured the mean bubble diameter. For that, another paper was published, and if anybody is interested in that, I can forward the details of that paper as well. And then I found that if then this is the formula of Fg. This is basically gas fraction. Gas Qg is the and Qg plus QL into 100%. So when Fg is changing, how D32 is changing. So this is like, so we can see that if gas fraction is increasing, we are like our mean bubble diameter is increasing. And here you can see I made some histograms, and here I made some PDFs and CDFs and bubble size distribution at increasing gas flow rate. Here also you can see. So this was the detail of the materials I used for my experiments for capturing data. Now let's move on to this plot. So I performed simple multilinear regression, and that is kind of Excel-based thing. And I calculated the values of A, B, and C, and then value of K. And then I plotted once again here. Like so, I found that the R square value was very high, like 0.998, for when I plotted the quantile curve for ln y and experimental and predicted. And when I calculate the actual values of D32, I found the values like R square is still very high, like it is 9.922. And that's how like I close this equation, and I can say, yeah, and this was the final equation of D32. So this, the first equation you can see here, this is dimensionless, I believe, if I'm not wrong, if I have not copied the correct equation. So this should be the dimensionless, and the second one, second equation is having the dimensions of L. So on the left hand side, we have the dimension of length, and on the right hand side, if you solve everything, you will find the dimension is also L. But this equation is not able to tell us like how these input parameters are contributing to increase or decrease D32. That is another thing. So I thought that I will perform a sensitivity analysis, and I developed some tornado plots. And here, like you can see, this is a tornado plot, and here in the x-axis we have predicted mean bubble diameter, and in the y-axis we have all these input parameters like Qg, QL, surface tension, and viscosity and density. So you can see here when the gas flow rate is increased by 15%. So this gray one is basically plus 15%. So we can call it increasing when it is increased by 15%. So the diameter is increased from 1.65 mm to 1.75 mm. When the liquid gas flow rate is increased, so what happened? Like diameter is basically reduced from 1.65 mm to around 1.6 mm. When surface tension is also having a bigger impact on the size of the bubble. So if you can see, like if the surface tension is increasing by 15%, so what happens here? Like bubble diameter is also increasing from 1.65 mm to 1.76777 mm. So that's how, like, that's why these predicted, like, sensitivity plots are very important. And for rho L and for micron, like, not much impact was there. So we can identify that, okay, viscosity and sort of density of the liquid is not having that much impact on the bubble size. Major impact is there on because of the surface tension and gas flow rate and liquid flow rates. So if we want to optimize our process, we have to first solve the problem related to these three parameters, and after solving this thing, then we should move to viscosity and density of the liquid. We should not start with viscosity and density of liquid. That is basically, so it is basically pinpointing the problem. So, and this type of thing, like when I joined STELCO, I'm doing this type of analysis a lot over there also, and I found it very useful. So I would recommend this to be done. Like whenever you perform any such analysis, like multilinear regression or artificial neural network, try to make a sensitivity plot, because that can give you an idea like where is the problem lying and how to solve that problem. So those type of things are possible. Now let's, but again, in this plot, you can see like R square value was just 0.922. And I thought I wanted to explore an opportunity so that we can increase this value further. So we decided that, yeah, and this is another thing I wanted to show to the students, like how you can perform that multilinear regression in Excel. So we have a data tab over there in Excel, and then we have data analysis. And when you open data analysis, you will find regression. And in the regression, you can put your input ranges like Y values and your output, sorry, your output ranges like Y values, and then X ranges like independent variables over here. And then you can determine like, and yeah, but after you hit OK button, and when once you find the result, you need to perform some tests like what is your adjusted R square, what is your R square, what is your P value. Those things you have to. If your P value is more than 0.005, it means like that parameter is not contributing that much into the value of like dependent variable. So you have to perform some test over there, and then only you can use it. Like you don't need to perform any coding, and you can solve your problems. So that's why I intentionally put this screenshot over there for the ease of the students. Okay, let's move on to the next slide. So I wanted to perform machine learning analysis, like machine learning model I wanted to develop in order to increase our R square value. And also, maybe in my previous model was related to multilinear regression only. So maybe we have because I performed dimensionless analysis, so I could capture non-linear correlation. But if I won't be doing that dimensional analysis, then it would be difficult for us to capture the non-linear correlation between those process parameters, like for example, gas flow rate, liquid flow rate, etc. So that's why we thought that we should go for artificial neural network, support vector machine, decision tree, and also multilinear regression to compare the results. Like, and then only we can perform yeah, then only we can decide, okay, like whether our previous model was completely okay or not. And also we could increase the coefficient of correlation, like R square, when coefficient of determination, R square. Yeah, but there was a challenge for developing this machine learning model. Like our number of data points were very less, like around 54 points we were having. So like we were thinking like we might be having high bias and like or maybe some variance is there. So some problem may be there with that data. So we should be having some more data points. So in order to increase the data points, we perform like and that can lead to underfitting and overfitting. So in order to avoid underfitting and overfitting, we decided that we will perform data bootstrapping, and then we will perform like k-fold cross validation. So like and that those two techniques are useful for ensuring that our model is not overfitting, because overfitting model is not good for any use. So let's move on to, and here like you can see like how we captured the input data, and that input data like these input variables went to the they were transported to physical model, and physical model was giving the mean bubble diameter by means of image analysis. And from the image analysis, we were having input output data, and that data was bootstrapped, and then we applied four different algorithms like decision tree, multilinear regression, support vector machine, and artificial neural network. And then we checked for overfitting, and then we compared the performance of all four models, and then we decided that okay, this is the best model for our case. Now let's move on to the next slide. So I wrote down, basically I make some notes here for the students. So I'm not going to get into this thing because it will take a lot of time, and these are kind of very bookish knowledge. People have this knowledge, and in the you can find it like from you can read it from here. Like this is all basically telling us like what is the how we develop the algorithm of decision tree, multilinear regression, support vector regression, and artificial neural network. And also, I'm saying that this is not sufficient. You have to go through more books, and like you have to get more knowledge about this thing, and then you can, and you should be having some programming knowledge also to implement these models. But I'm not going to get this thing. Okay, I'm not going to talk about this thing over here. It will waste our time. Okay, so and here also I have noted down for the student for the sake of like students. I wrote down the what is k-fold cross validation, why we needed this to be used, and what was data bootstrapping, why we needed this to be used. And all these things I wrote down, and like students can read it after that if they want to study, like if they want to make their career in machine learning, I would say. Okay, let's move on to the next slide. So these are some results. So here you can see when we were using single linear regression model, and here we have single decision tree model. Here we have single ANN model and single SVR model. Why single model? Because when we don't do bootstrapping, so that model is basically single model because no aggregation is there. And when we perform bootstrapping, that time we have like we call it aggregation model. So in the aggregation model, if you can see like training and validation is quite close to each other for all the cross validation split. Like one, we performed five fold cross validation, and like these are very quite close to each other. So, and here also we have this training and validation, and this is for the SVR. So we could select any of these two models because we can see, and also validation is far more lower than the training over here. That's why we did not choose this one. So it looks like this is kind of a high variance type of, so some overfitting maybe there. So that's why we did not use this one because for training model was very good, but for validation it was not that good. But in these two models, like for training and validation, they are close to each other. It means they are quite good. Same thing happened in case of DT also. So that's why we rejected the above two, and but we took the second two. And you see, after the bootstrapping, like our model is better than the without bootstrapping. You see the difference between the gap between the two plots. And then we see our cross validated R square. So for SVR and ANN, we saw that we have higher R square value compared to MLR and DT. Okay, so that's how, and let's move on to the. So for ANN, we also did some feature selection study initially. Like so, for that we use the function of core plot, and then for developing our ANN architect, we decided like we wanted to perform like a number of neuron optimization. So you see till here, like those validation and training are very close to each other. So we took the 10 number of neurons over there, and this was our final architect. We used this thing for making our new model based on ANN. And here you can see the result. So that was the quantile plot for ANN model, and this is the quantile plot. The blue one is for the MLR model. And you see R square was increased to 0.955, and the initial one was just 0.9179 or 92. So we got some like improvement over here. People were saying that R square of 0.92 is also very good. So why you want to increase it further? But yeah, if we have a chance to increase it, because in some like we will see in our upcoming slides that R square is only 0.63. So sometimes if we have a lot of data, that time our R square goes lower because a lot of anomalies are included in that data. But this data was captured in a lab. Atmosphere was quite controlled. This was not plant data. So for that, in such conditions, our R score should be higher if our model is robust. So that's why we wanted to perform like we wanted to use machine learning. And then I made error histogram of ANN and MLR model also. So you can see like ANN PDF is this like, so the distribution is not that scattered. But in case of MLR model, like it is little bit more scattered. So it looks like that when we use ANN, some error was reduced. So that was kind of a result of ML model in that study. Now let's talk about the second study. This is model for dephosphorylation in basic oxygen furnace. This is also pretty interesting study, and this paper was published in 2019. And so here we talked about like how why this like in this paper like we predicted the coefficient of dephosphorylation, and some previous equations were already present, and but those values were having more error, and we wanted to reduce the error by developing a new equation using machine learning models like data driven models. So, but what was the problem statement? So, dephosphorylation of steel is critical due to rising prices. Like we have observed that 100% price rise has been taken. 100% rise in has been observed in past 5 years in the price of iron ore in North America. it has been seen. So which has resulted in the use of lower grade iron ore. So people have to use lower grade iron ore, otherwise they have to pay, like steel price will also increase. So which is people don't want to pay for that. And then the second one is increased phosphorus content in steel imparts cold shortness. We know from our mechanical metallurgy and then physical metallurgy, and leads to poor ductility, toughness, formability, and embrittlement. So thus BOF process times increases. And also what happened, like because we cannot afford that high phosphorus, so we have to reduce it, and so because of that BOF processing times are increasing, like, and if the processing times are increasing, so in one day you cannot produce, suppose initially you were producing 30 heats per day, and if your processing time is increased, now you are producing only 25 heats per day. So your opportunity loss is corresponding to those 5 heats, and one heat is of 200 tons or 250 tons. So you are not making around 1,000 tons every day. So loss is like billions of dollars. So we cannot afford it. So just a small thing is giving us the hard time. So this is not acceptable. Then so what we observed that implement, we have to perform, like some things can be done to control, to reduce these problems. Like we can do some infrastructural like infrastructural changes in the plant, like we can apply sublance, we can develop dynamic process models, but those things are also costing some money and it takes time to get approval from the senior management. So it's a good idea to perform, like to do, like to think about the lower hanging fruit, which can be, because that can give us quick benefit. So that in compared to the conventional thing or the more robust thing, like it is not like comparable to that, I would say. But still I can say that if we have some idea, if we can implement something quickly, if we can get the money, because like money rollout is very important. Like if we wait for getting the money for long time, so like we are not able to invest that money to earn more money. So we have to do something so that we can get the money right away. So that's why we thought that we should implement the ML model, and which can help to predict the phosphorus partition more efficiently, which will provide a robust process control. And in last few decades, several predictive models have been developed already, but most of them have some limitations, and their correlations are not that good. They have reached up to the R square value of zero point 0.6, zero point 0.5 maybe, but those are still very, very low. So we thought that we will perform machine learning analysis data. Now, how we develop that models, like model architecture. So we simply used multilinear regression uh, along with k-fold cross validation. And then we performed individual predictor analysis as well, like simple linear regression for individual parameters, like what I showed you, like core, like in the previous thing, in which I used core plot function of MATLAB. And then we identified the influential observation and outliers, like which are affecting our correlation coefficients too much. So we wanted to remove them, and we performed DF fits values. Some formula is there, and based on this, we excluded those outliers. And we also used GLM, because we are not able to. Sometimes what happened, like MLR, there is a problem called heteroscedasticity. It is kind of a very difficult word to pronounce. What happened, but to make you understand, make you understood, I can tell you, like sometimes what happens whenever we are curve fitting something, so some losses are there. So what happened, in order to match those losses, we introduce some correction factors. And what happens sometimes, those correction factors are good for one range, but those are not good for another range, and so errors are increased for different range of data set. So that time what happened, heteroscedasticity is introduced in the model. So that time we avoid to use MLR, rather we use GLM. The detail of GLM is already given in that paper, so you can go through, and also code related to that is also available in GitHub. We can talk more about it later. And then we got some results. So this was our final equation. This was kind of 100th equation for the phosphorus partition. And yeah, one good thing about this equation is like we could capture the effect of vanadium oxide and titanium oxide. In the previous equations, these values were not captured. So machine learning helped us to identify these two values as well. And these are the like quantile plots. But our R square value was not that high. I accept that. Like our value was only around 0.63 point. But previous models, their R square value was lower than ours. So I can say I'm not that good. I'm not the best, but I'm better than them. I can say in one way. And then understanding dephosphorylation and this is the paper. Like you can go through this paper, and these are our co-authors. And when that paper was published. And yeah, let's move on to the yeah. So we made some waterfall chart also. So like waterfall fall chart is another way of representing the effect of individual contributors. Like one way of doing that, like making a tornado plot. So if people are going to the like going in the field of data analytics, they can use a sensitivity plot, or they can also use these like waterfall plots. So you can see that if calcium oxide is increased by 1%. So the LP, like phosphorus partition coefficient, is increased by this value plus 0.021. So all these values, this is how like we read waterfall chart. And yeah, one more thing I forgot to tell you guys, like we compared this data for plant one and we had the data of two different plants, plant one and plant two, and we performed separate analysis for both the plants. Like we did not add the data of two different plants. Why? Because kinetics of those two different plants are different. Like one plant was having different capacity BOF, the second plant was having a different capacity of BOF, and their operation practices are also different. So kinetics are different. So if we would be including both the data sets, so it might be leading to less R square value. So that's why we did not take chance over there. So we performed our analysis separately for plant one and plant two. Okay. Another thing here that you can see our results. So for plant one, we didn't our R square value was only zero point 0.5. It's not that good actually, but other you can see other equations like they have got only 0.48, like less than that. And in the for the plant two conditions, like yeah, and you will ask like so we applied same equations on plant two and plant one, same equations. So there is a glitch over there, like because those people have developed those equations for their plant or their data, whatever data, and we use their equation on our data. So maybe that is the reason of reducing R value, because as I said, that kinetics are different from different for different processes. So that may be a reason, but I'm not sure. But still, you can see like R square values are quite close to 0.62, for many equations, and in here we have got 0.63. So this is one way of showing it. Yeah, but still a lot of research is required, and like I invite people to do some like more research in this area. Okay, and then we can make it more robust. Okay. So now let's move on to our third topic, which is hybrid model and endpoint prediction in BOF. So what is the problem statement? Like an optimized BOF steelmaking can increase the metallic yield. Like when we are making heats in BOF, so our main objective is to optimize the steelmaking. Okay, because what is more important is metallic yield. How much liquid steel we are getting when we are charging X amount of hot metal and scrap and so how like so that metallic yield we calculate, and that metallic yield should be like always be very high. Like in the senior management, like CEOs and CEOs, whenever they ask for the performance of the model, they see only this value, and they are concerned like only about this value, like about what is our metallic yield going on. And if there is a loss of 0.1% of metallic yield, there is a pandemonium in the plant. I can tell you my from my experience, like people are like saying, "Oh my God, point we have lost 0.1 because 0.1% is causing like lakhs of rupees or maybe crores of rupees." So that's why it is very critical. So that optimization is also very important, and that is also the responsibility of a process metallurgist and process engineering, especially engineer. So those people are the people like who will do that thing, and then reduce. And also, what will happen? if process times are like metallic yield is lost, it means in every heat we have lost some steel somewhere. Maybe it is going to the slag or it is oxidized. Something is happening over there. Second thing is reducing processing time means if processing times is reduced, it means like we are producing less heats in one day. Initially, if we were making 30 heats, and on the second day, if we made only 29 heats, so it means we lost 250 tons in like and 250 tons when we would be converting that into a finished product, like 1 ton is causing like 50,000 rupees. So 250 tons you can calculate. So that much money is reduced. So that's why processing times we have to optimize our steel making. Then slag volume has to be reduced. Like it should not increase because slag handling is another process which is taking place over there. Then improve phosphorus partition, and maintain end temperatures. A lot of things we have to take care of. This is another problem statement. Then optimized view of steel making can also help in increasing the campaign life of the vessel. Suppose if we are running our BOF at higher temperature all the time, so what will happen? Refractory will go bad. So you have to change your refractory. Refractory life will go down. So if you change the refractory, like your campaign length will be short, and campaign length, like so you will go for shutdown for more time, like 2 3 days, like more frequently. And more frequent shutdown means you are losing production for those days. So that is also important thing. Third thing is many of the old BOF plants are having dynamic and are not having plants. Dynamic and operation models are not installed. Yeah. So dynamic and so when we are buying new BOF plants these days, so suppliers are providing dynamic endpoint prediction models, and for that they provide respective equipment as well. For example, they give us sublance, which can which can give us the data of like dynamic data of per heat. But in the previous plant, in the old plants, which were installed like 40 years back or 50 years back, those facilities were not there because those facilities were not invented. So but it doesn't mean that we don't do anything. We have to do something, right? So we decided that we will develop a static model, and that will be static endpoint prediction model, and that will, with the help of, we will include like we will, and why we are calling it hybrid. You can see I mentioned the word hybrid here because there were some theoretical models in place already. So we just combined the theoretical models with the machine learning models so that both of them can overcome the limitations of each other. So that was our idea of doing so. So let's see like how what was the model architecture. So here you can see we have theoretical endpoint model, like with the help of heat balance, mass balance, thermodynamics, all those principles. We calculated the carbon percentage per heat, and then temperature per heat, phosphorus per heat. We also develop a slack chemistry model, and then these two values are going to a specified input data set. And then we perform on the same data set, we perform artificial neural network based machine learning model for carbon, for temperature, and phosphorus respectively. Then we applied five-fold cross validation once again, and then that data went to that common place, and that was basically our hybrid model. So these are the details of Slack chemistry models. I'm not going to get into the details of this thing. Everything is mentioned over here. Uh, Second one is the detail of our endpoint carbon model. The endpoint, like what we did basically, we performed mass of oxygen injected, like we calculated the mass of oxygen source and then calculated the mass of oxygen from Slack chemistry, then determine the amount of oxygen used for decarbonization. And then that's how we calculated. These are all related to our theoretical model. We performed heat balance as well, and for the heat balance we calculated like this endpoint temperature model we developed. And then like phosphorus model already we had, so we used the same model. We did not calculate anything new. Yeah, but we had new data sets, so we used the new data set on our old equation. So that's how we calculated the phosphorus model. And once that hybrid model was ready, we compared the performance of non-hybrid model, like just machine learning model and hybrid model. So we saw that there was some improvement when we make the hybrid, like in some cases, like for in case of phosphorus, non-hybrid model was better, and that equation we took from our previous study. And for yeah, this is basically our, this is machine learning model. This is our mechanism model. MM means mechanism model. So when we use for the mechanism model, like non-hybrid model was okay, but yeah, and for ANN model also our non-hybrid model was a little bit okay. So that was our idea, but yeah, uh, that value can go down basically. That can increase more error. So that's why it is a good idea to develop such hybrid models, but sometimes you don't get results, I would say. So it looks like that only because this for in case of yeah. So you can see this is sorry. I want to change my words. So this is basically errors. This is not R square value. So errors are always lower here. You see, in case of mechanism model, error was more than the hybrid model. Like non-hybrid error was more than the hybrid model. So that's why errors are less. That's why it is a good idea to make hybrid models. So what is the summary of the presentation? Machine learning models can provide better results if sensory data is accurate. Yeah, this is very important because sometimes what happened, like you are getting all the sensory data wrong all along. And you don't know that because you are not talking to the plant people. You are sitting in your office or in your lab all the time. You are not going to the plant. You are not talking about the things. So nobody has informed you that okay, that particular sensor was wrong for 6 months. So please don't take the data from that. So if you do so, so that's why you have to talk to the people more and more so that these things won't happen to you because all your hard work will go in vain. Then mechanism models are dependent upon the kinetics of the process. So one model may not work for another process. Then hybridization of mechanism model and ML based model can reduce the error of the final model, and appropriate ML model can improve the accuracy of correlation obtained by other data-driven models. These are our papers. So I will forward this presentation to Dr. Dinda, and and you guys can go through these papers. And if you have any questions, you can get back to me. Thank you very much. That was the end of my presentation.
Thank you, sir.
Yeah, if you
Now
have
the
any questions.
question hour is start. Anyone have any question? Please raise your hand. I will unmute.
Hello, good
Yes,
morning,
please.
sir.
Good morning.
Sir, what is this five-fold cross validation or tenfold cross validation?
Yeah, so actually, sometimes what happens, like our model can be overfitted, right? So or underfitted. So because sometimes what happened, like we have less amount of data. So if we perform this cross validation, so I wrote down the details of all that thing. So I will give you the presentation. You will find out. It is very easy.
So
Here
what
I
does
have.
this
Yeah,
fold
that's why
mean
I did
here?
not touch base with this. Pardon?
What does this fold means here? Like fold cross validation. So what does it mean?
Oh,
Like
so
what is?
folds are basically split. So suppose we have only 100 data points, right? So 20. So what we will do, like we will make two data sets. Like one is like 80 data set. Like if we are taking the percentage of 80 to 20%, so training data will be 80% and test data will be 20%. Some people can do 70% training data, 30% test data. And after that, what will happen? Like that 80, we will if we are doing the five-fold cross validation, so we will divide those 80 data points into the sets of into five sets. So 80 by 5. So 16 data sets, data points will come in, or data sets will come in one fold. Another 16 will come in fold 2. Another 16 will come in fold 3. So that way, if you add up all of them, you will get a value of 80. So fold is basically split of data set.
Okay, so we train our model with each fold.
Yeah.
Okay, thank you.
Okay, no problem.
Sir, my question is, in cluster, you said that the bubbles formations, greater size bubbles is regarding for the defects like pencil pipes or blister formations. Can
Yeah.
it is also regarding for the defects like hydrogen? It is only on nitrogen or on
No, this is
any
only
bubbles.
organ. We inject organ over there. No, hydrogen is not there at all.
Yeah, only argon.
Hydrogen
Argon
can
flow
be,
rate
yeah,
and
hydrogen is not injected like
yeah,
intentionally. We
only
cannot,
argon
yeah,
injected.
yeah, only organ is injected. Hydrogen, but hydrogen can be dissolved inside. Like 2 ppm for slab casting we have an equipment called hydris. Like in my previous company we had an equipment called hydris, and we were measuring the hydrogen content of each heat, and also in the tundish and in the mold also we were measuring hydrogen content. So we have to maintain the content of hydrogen, and that can lead us to hydrogen related defects, but those defects are different from this defect.
Yeah,
This is
in
here we are only
dephosphorize
injecting organ, that's it.
in BOF dephosphorylation, whatever you deliver this model, it is
Yeah.
100% accurate, or that is something
So as I
error.
said that we are, yeah, it is like you see for the dephosphorylation model, like our R square value was around 0.63, like for plant 2 data. So I would
No,
say
sir,
it is not that,
please,
yeah, but it
please
is
see
best in
the
the market, I would say. Pardon?
please see these equations, that is LP. No, sir, another side.
Yeah, let me go there. I'm trying to find out. Yeah, here it is, right?
LP percentage. This is
Yeah.
LP equal to 15.2 for this. In this equation, we are put in this equation. Then we get our dephosphorylation.
Right,
We get our
right.
LP.
So if you have Slack chemistry with you, so you can just put down your
Yeah, yeah.
plug in Slack values over here, and you can find out this value. This is the most latest
If,
equation. Maybe after 2019, some people have come up with new research. So the new, but I haven't checked for so long. So maybe some new research, but compared to all other equations developed before this one, like it is the best one, I would say. But yeah, it is not that good. So we need more research to be done. Like for example, for future study, we can do like we just use MLR equation, MLR here. So
no,
yeah, we
now
could
sir,
use.
I am working on BOF. Yeah,
Okay,
or one more question is,
yeah,
if the nitrogen pick up in BOF, some case I have seen the nitrogen pick up
hmm,
in BOF, that is 20 to 30 ppm. Then it
yeah.
will go another step, that the secondary metallurgy. Then after we will go to the casting, the nitrogen
Hmm.
ppm will be higher side. This is
So
called the
maximum,
bubble.
what
This
nitrogen
is
value
called the
you
bubble
see in your
formation.
viewer? Pardon?
31 ppm.
In your BOF, though it is not that bad, I would say.
No, sir,
Yeah,
this is not bad.
yeah.
I think this is not bad. But whenever we are going to processing these heats, then the nitrogen pickup will getting higher. In whenever we this heat will casting, the slab
Yeah,
nitrogen ppm cross to the 40 50 ppm, which is not is which is bad for the interstitial free grade.
right. Yeah,
Yeah,
you are
how
making
can
IO
how
grade. That's why. Yeah, that's why you are. Yeah,
yeah
yeah.
yeah.
So actually, the thing
How
is
can
that you can control. Yeah, BOF you can control nitrogen over there, but after all your processes, after BOF, you have your ladle furnace, you have your ARS station. So and then you have your tundish, you have your mold. So all those places you have to find out where from nitrogen is getting entrapped. Hmm. One example I can tell you, like what happened if we take the example of this mold. Let's get back to this, like
yeah
there you
yeah
can
yeah
check. Yeah, let me show this thing. Oh, sorry. Yeah, here it is. So in this one, if there is sometimes what happened at the joints or so some negative pressure is generated over there inside this mold, right?
yeah
Inside this SEN. And because of the negative pressure, a lot of nitrogen is getting entrapped into the steel. So in order to avoid that, we do some like organ purging, and that organ purging helps us to like block those openings. So that is one. So there are many places. So you have to identify all those places, and and also if your nitrogen is very high and if your customer allows you to add some titanium, so you can add some titanium that will help to scavenge your nitrogen. So it will make titanium nitride. But yeah, titanium nitride can be detrimental to the property of the steel. So, like maybe for IF grade steel, like how much titanium you are allowed to add. That I don't know. So you can check for that. Okay.
Sir, bubble size is also responsible for this or not?
Bubble size for nitrogen pickup, I have to think about it. I don't know right now. Yeah. Bubble size, I don't know. Maybe I will think about it. In case of maybe in case of ladle, it might be, but no, I don't know. I don't know that thing. Yeah, I haven't looked at it that way.
Only sir, bigger bubble size, which is going to the same
Oh
to the
yeah, that
mold.
is another thing. Yeah. Bigger bubble size can make open eye, and from open
Yeah,
eye,
yeah,
air can be trapped.
yeah,
Okay,
yeah,
yeah. Oh,
yeah.
sorry, I forgot that. I told in this. Yeah, I mentioned that thing. I forgot that. Yes. Yeah.
Yes, sir. Always, sorry, sir. For this cause, even the bubble size is responsible for this.
Yeah. That is possible. Yeah, and you know what? OpenEye can be formed in the condition as well. It is not like OpenEye is formed
Yeah,
only in mode. OpenEye is formed in the formed in your
condition.
ladle also. In ladle also. Yeah.
Yeah,
Actually, like very first time OpenEye studies were performed in ladle only. After that, people extended that knowledge to Tundish, and then people extended that that knowledge to mold. But in case of mold,
oh,
you will
yeah,
not see many studies. Only 2-3 studies you will find, and one of my studies already also included in that.
yeah. Okay, sir. Thank you, sir.
Thank you very much. Any other question?
Any other question? I think this is no more question. Thank you, sir, for your nice presentation.
Thank you very much for inviting me to this workshop. I'm very happy, and I will come next time also.
Okay, Dr. Amiy. Okay, see you then later.
Yeah, sure. Thank you very much. Yeah,
Okay,
have
Sir,
a
sir.
good
sir,
one.
sir,
Thank you
hello,
for
sir.
your time.
Yeah, no problem.
Sir, hello, sir. Can I
Tell me.
contact you, sir?
Yeah,
Can
you
I
can have my
contact you, sir?
contact from Dr. Dinda. You can have my contact from Professor Dinda, and he will.
Yeah,
Where
yeah.
are
Okay.
you from? Are you doing PhD or like?
I'm doing PhD now, but currently I'm working on Tata Steel.
Tata Steel, Jamshedpur or Kalingnagar?
Yeah, Kalinga.
Okay, good. Okay, yeah, you can take my contact from
Okay,
Mr. Dr.
yeah.
Dinda.
I will share with Deepti Ranjan. Don't worry.
Okay,
Sure.
okay, sir.
Thank you very
Okay,
much.
sir.
Thank you.
Okay. Thank you, Amiy.
Thank you very much.